a new chapter. This is called semi. So it is a material, you can say, having the connectivity less than or much less than conductor, but more than insulator. So it's somewhere in between. So the question is why we need to study this chapter. What is the motivation behind studying this chapter? Anyone, any idea? So the answer is very simple.
Computer chips.
Yeah, of course we made it. But the thing is, what is the purpose of using this in computer chips? Okay, we have a better conductor, which is metallic conductors. But why we need the use of semiconductor?
For controlled conduction, like we can enable and disable the conduction whenever needed.
So that is a perfect answer. It's the control. Okay, so we always looking for control because in metal control is not possible. The moment you apply even a slightest voltage, current will establish. So there is nothing like a cutoff that beyond this it will start or it will not start. And not only that, there is no way to control or you can say increase or decrease the conductivity. Now this issue can be solved if you use semiconductor, that it gives you a control access to the current, voltage, and various things. And because of this particular reason or this property of control action, you can create a embedded system in which you can manipulate other event just through the current and voltage externally as well as sometimes remotely. So that benefit is there. But the problem is we need certain connectivity. So a very poor conductor, let's say if it is a really weak conductor, then again it is of no use because for functional purpose, we do need certain connectivity. And because the most pure form of semiconductor are as good as insulator at a very low temperature. Only at high temperature, they exhibit some sort of connectivity. But that connectivity is not sufficient to create any practical purpose device. So the entire purpose will not be met. And therefore, a very pure semiconductor is of less practical use. We need to somehow do some changes to its internal structure in order to enhance its connectivity. Not very large value, but to an extent which can make it more controlled and meaningful and useful at the same time. So the form of conductor, the form of semiconductor, which is in the purest form, is called intrinsic semiconductor. And the form which is not so pure, in which you add something, okay, is called the extrinsic semiconductor. Extrinsic you can also call impure, but here the impurity is a desirable impurity. Okay. What happened? My voice is not audible. Hello.
Not audible.
Inaudible.
So, okay. All right. So the whole idea is the impurity is a desirable one. We need to add something to make it or enhance its connectivity so that we have a better, you can say, control over the current flow and all. And also the current is sufficient enough to make some changes to the, you can say, voltage and current to a value which can be determined or detected by the other device. So the whole idea is this one. So the world of semiconductor is to create a control access of things. Okay. And by converting every event into 0 and 1, if you code as a binary, then we can actually control the every, you can say, binary decision. And a binary 1 to a machine is like a slightly high potential, and a binary 0 is like a low potential. So we can actually mimic this binary behavior by setting a threshold. And once you set the threshold, then beyond the threshold, you have one region, and on the other side of threshold, you have another region. And by well-defined threshold, we can have a world, divided into two parts, one above and one below, and that's why we call this as a binary decision boundary. Okay. Now, this binary behavior is of great use to create all the, you can say, microchip, processor, whatever, motherboard, and everything else. Now the entire world is running on microprocessor chip only, the semiconductor chip only. So whole idea was threshold, and this threshold was missing in which case? In case of conductor, because in conductor we don't have any such threshold, you can say, behavior. So now luckily we have. Okay. And as I said, the world of semiconductor will take care of connectivity. It will keep the connectivity neither very large nor very small. It will have somewhat meaningful. And if it is really small, we can enhance it by a process called doping. Okay. What is doping?
Adding certain impurities to semiconductors to increase their conductivity.
Correct. So doping is simply you add some, you can say, element. You make it impure in a way, but it is very desirable effect to produce the desirable changes. Like you increase the connectivity to a limit, okay, certain limit which is useful, okay, for the purpose. So which element in periodic table belongs to semiconductor? Which group of elements? So if you go by the older convention, then
4A.
the group 4 elements. Okay. So group 4 elements are what? Carbon, silicon, germanium, stannum, plumber, right?
Yes, sir.
So as you go from top to bottom, we have a non-metal, and then we have a semiconductor. But as you go deep down, the property will turn into metallic property. So the silicon and germanium are very famous semiconductor. Now, who are the neighbors of these elements? Who are neighbors?
Group 5 and group 3.
So the elements of group 5A are
Nitrogen,
Nitrogen,
phosphorus.
phosphorus, arsen, SB, and Bi.
so this is the group 5A elements, and the group 3A elements are
Boron,
Bal,
aluminum, gallium, indium,
K.
gallium.
okay. So now the question is why these neighbors are important. Okay. So we know that in periodic table, as we move across the table, the size changes, right? So the size will change, and as you go from top to bottom, what happens generally? From top to bottom, size will grow in
Increase.
value,
Increase.
and left to right.
Decreases.
Decrease.
So left to right it will decrease. So increase, decrease. So if this is the decrease axis, and if it is the increase axis, then an axis with constant size will be something like this, isn't it? So as you move across it, you may expect some sort of constant size effect. So can I say this size will be somewhat more similar, isn't it?
Yes.
So it will decrease as you go right, and it will increase. So it is possible that this may be equal. Okay, I mean that is just a very basic idea. The idea is the doping process is a desirable event. So we want to dope the, pure semiconductor or intrinsic semiconductor, and the purpose of doping is to add elements in order to increase its connectivity to a desirable value. But the thing is, Doping also means replacing the pure atom. Okay, the actual semiconductor, the pure semiconductor. So you want to replace either silicon from the crystal point or the lattice point, and you want to replace by some similar size atom, isn't it? And the similar size atom you will get only from the neighbors. Okay. So you have two choices. Either you can add the trivalent element or the pentavalent. So what will happen if you add trivalent, and what will happen if you add pentavalent? What will happen? Tell me. So adding trivalent and pentavalent will make some changes, isn't it? So you need to know, first of all, a silicon will act as will exist as a crystalline
Networks.
lattice network, right?
Yeah.
And everyone will, share their electron, and they cannot participate in, exchange of electron because they have the valency issue. So now this will share with this, and this will share its. So all will try to complete their virtual octet, right?
Yeah.
Okay. So this is the bonding. Now suddenly one fine day you decide to knock out one of the silicon, and instead of that location you want to put some other element. Now which element will fit into that space? Okay. The answer is the element from the neighboring column, isn't it? That's logical,
Yes, sir.
because only neighbors can be of same size, isn't it? Tell me, guys.
Yes.
So for group 5, group 4, we have two neighbors, 3 and 5. And if you bring the 3A neighbor, the problem is once 3A will come into picture. So let's say you bring the aluminum or maybe boron. So rest are silicon as it was earlier. Now what will happen? So don't see, you're not supposed to write anything. I'll give you the notes at the end. Because it's a really big topic. I can keep on teaching for the 6, 7, 8 lectures, but if you look at the schedule, I want to finish in 2 lectures. So don't write anything. I'll give you all the necessary notes. So anyway, let's do once again. But boron as an element, if you know, will have only 3 electrons to share. So the boron is also called the banana guy, right? B2S6.
Yes.
Banana bond. Anyway.
Yes, sir.
Now the problem is the boron cannot participate in bonding with silicon unless it will not acquire somewhat one extra electron. So what it does is technically it will break some covalent bond in the metallic lattice. So you break one bond, and it is said that breaking of one bond releases one electron and one empty space, which we call hole. You can think this way. So a breaking of bond creates electron hole pair. What we say? So breaking of bond creates electron hole pair. So what this boron will do? It will acquire this extra electron from somewhere. This is the acquisition. Now, as a result of acquisition, what will happen? The boron will become negatively charged particle, yes or no?
Yes.
And not only this, it will leave one hole unattended. It will leave one hole unattended. Understood what I'm saying? So now this will participate in bonding again, and this is left to roam. Left to roam. So which kind of charge carrier it will create? Now this will become the carrier. charge carrier. So which kind of charge carrier we have? We can say we have the hole as a charge carrier. So by convention, holes are assumed to be positive charge carrier, because if electron is negative, then you can say its opposite will be holes, which are positive charge carrier. So addition of trivalent element into the pure semiconductor will create a new semiconductor in which the majority charge carrier will be whom? Like who will be the majority charge carrier? Who will carry the
Holes.
charge? It is the hole. Isn't
Yes,
it?
sir.
It is the positive charge. So that's why when we obtain this impure form of semiconductor, we name it P type or positive type. And how we represent this? We represent by draw a big circle, put a minus and a circle. This is like a fixed lattice point. And the hole shown above is representing the roaming particle, the free charge particle or the carrier. So the P type is clear. What is P type and how it is obtained? It's very simple. You add the neighbors of group 3. I mean neighbors of group 4, of course. So if you add the element from the group 3A to the pure semiconductor or the intrinsic semiconductor, what you get is extrinsic semiconductor with a charge carrier as whole. Now, when I say charge carrier, then I mean to say the majority charge carrier. Now, holes are the majority. Who will be the minority here?
Electrons.
Electrons.
The minority here will be the electrons. So it means a semiconductor will always have both charge carrier, but the thing is one will be the majority, other will be the minority. So in P type, it is not just the holes who will dictate the conduction process, rather it is the electron which dictates the conduction process as well. So the net conductivity of P type depends on both the charge particles. So hole is assumed to be a quantum charge particle. I mean, it is proven quantum mechanically that it's a charge particle, but physical existence of this, I mean, it cannot be observed as a particle, but it is okay coming theoretically also and experimentally also. To understand that what exactly is hole, I'll tell you one very nice example. Hopefully, this will help you understanding holes. So imagine you guys are at home, your parents are also at home, and you enjoy certain degree of freedom at home, isn't it? So there is certain freedom associated with you as a, you can say, a small kid when you are at home. Now, due to some reason, your parents goes away from your home. You are still at home. Can we assume that your degree of freedom, I mean, the extent of freedom has gone slightly up
Yes.
because of their absence? Can you see?
Yeah.
Now, the same thing happened that the conductivity of a doped conductor is found to be more than, okay, I mean, this is the P-type semiconductor you have. And once you make this doping process, you suddenly realize that, okay, the conductivity has gone up. Now, there are two ways to compensate for these changes or to justify the change. One is you can say that electron will have a dual character in terms of connectivity. It behaves or gives certain connectivity in less freedom condition and more connectivity in the more freedom condition. But this is a bad way of assumption, because I'm having one particle with a different characteristic in different context. Now that kind of analogy will make it really complex in terms of mathematical explanation or analysis. So what we thought of, keep the electron as electron, and think of this additional freedom as an additional particle coming into picture. So the additional freedom, or you can say the change of conductivity is attributed to a new variable, and we call this new variable as holes. Okay. So that way of assumption will get rid of a variable property of a given physical entity. Are you getting my point? What I'm saying?
Yes.
Okay. So the hole is like a, you have assigned this extra conductivity to this new, okay, imaginary particle as of now, but it is quantum mechanically proven that it's a particle. It does exist. How? It's difficult to explain. So similarly, what will happen if you add the neighbors from the 5A group, you can say group 5A. So if I have a replacement from the neighbor from the right, let's say if I choose arsenic. Now arsenic will come with how many electrons? Tell me, guys.
5.
But how many electrons you need to make the patch up with the neighbors?
4.
So what will do with one electron? You will simply release.
It will roam free.
Yeah, it will release into the lattice. So now these will participate in the bond formation. They are happy with the octet, and arsenic will release one of the electron to become As plus. And therefore, this will lead to a formation of a new type of semiconductor, new type of extrinsic semiconductor. We call this as N type or negative type. I think this is very simple, right?
Yeah.
And this we can represent as a circle with a positive lattice. So whoever acquires the lattice, we represent the sign of that new guy. And we put the charge here as a negative charge, or if you wish, or you can write as plus with electrons. Whatever is your choice, you can go ahead with the notation. Okay. Now the next question is how much we add. The answer is we add in parts per billion and parts per million. You know parts per billion means?
Yes.
Yes.
So the replacement is out of 1 billion atom of silicon, I'll just choose one of them. So for every 1 billion atom, I will add how much impurity? Only one. Okay. So only one boron or only one arsenic will be added. So we are not going to replace each and every silicon. We'll move in the lattice, and for every billion of silicon atom, I'll replace one of them. So it might looks like this is a small number, but it turns out to be this is huge number. And the question is why? Why this is such a huge number? Any guess? Hopefully.
Sir, 1 mole compound, 1 mole amount is like 10 power 23 order, and this is like 10 power 9.
Yeah, correct. So it is still humongous replacement, right?
Yes, sir.
So the thing is, the intrinsic concentration we call Ni. This is called intrinsic concentration of holes electron at a given temperature. So you will come to know something that every pure semiconductor will have equal number of holes and equal number of electrons at any given instant as a free charge carrier. So it is like they exist in dynamic equilibrium, which means the count of electron and the count of hole will remain constant, which means the rate at which they recombine to form the bond and the rate at which the bonds are breaking into these elements will acquire some equilibrium distribution, and this equilibrium distribution will vary with temperature. So for a given temperature, it will have one particular value, and this value remains constant. This value remains constant. Okay. So of course, there is a formula for that also. There is a formula that Ni equals to some constant T power 3 minus, so there's some formula like this. Eg naught, I will come to this. What is Eg naught? What is K? K, you know, this is Boltzmann constant, and T is temperature, A is some constant. Okay. So anyway, the idea is there is something called intrinsic concentration, and the value of intrinsic concentration is really high. So the number of electron or number of hole which actually exists is 10 power 16 per meter cube. So these are number of holes and electron which is always available in the pure semiconductor. Okay. So what happens if you add some p type? When you create some p type. So to create some p type, what you do exactly? You add some group 3 elements to the pure semiconductor, right? And the moment you add the group 3 elements to the pure semiconductor, what will happen? What you're adding? You're adding holes in excess, isn't it?
Yeah.
So those extra hole will eat away those extra electron in the entire distribution. It is like they will recombine with the existing electron and will become bond again. So you disturb the concentration, right? Now what you disturb? The intrinsic concentration will change, isn't it?
Yes.
So what will increase and what will decrease? Relatively. Earlier, the electron concentration and hole concentration was equal. Addition of p type, okay, what will happen? If you add a group 3 element, what will happen?
Number of holes will increase.
The hole will eat up the electron. So the relatively hole will become dominant now.
Yeah.
See, holes are coming to eat up electrons. Holes are coming to eat up electrons.
Yes.
So relatively electron will decrease. So we can say relatively holes will increase. Okay. So anyway, we'll come to that. But before that, we need to know something even more basic. Okay. So there's something called band theory. Band theory of Schurz. So we all know something called Bohr's theory, right? In Bohr's theory, we talk about the isolated gases atoms, isn't it?
Yes, sir.
In Bohr's theory, what we study? Isolated gases atom. Then after Bohr's theory, we go to something called MOT, the molecular orbital theory. And here we talk about the node and antinode, right?
Yeah.
So here we talk about the molecular orbitals, not just isolation. So a molecule is cluster of atoms, right? Although in a small number, but molecule represents always a group of atoms. And when they come together, so we know that the orbital is nothing but a probability wave. So can we say coming of atoms together is superposition of the probability wave of each atom? Isn't it? You can think this way. So when atoms come closer or together to create any molecule, there is an indirect superposition of their molecular orbitals. Yes or
Yes.
no?
Yeah.
And as a result of superposition, these energy levels, which were, you can say, every atom will have its own very, you can say, discrete and individual energy level, when they come together, they mix up. And once they mixed up, then it is difficult to distinguish which energy level belongs to what. But anyway, in the molecular orbital theory, we study that, okay, these energy will split into two parts. One is the low energy shell, another is the high energy shell, or not shell, you can say energy levels. And these high energy levels we call antinode and low we call node, isn't it?
Yeah.
And we know that more the superposition, more the splitting will occur. So we have pi bond and we have sigma bond. This is what we study, right? So how the sigma bond will overlap? Directly. So among pi and sigma, which will overlap first?
Sigma.
Sigma. So sigma will overlap and it will split. Okay. Now there is something very interesting. The pi also overlap. In fact, if you remember the theory, for elements having atomic number less than 14, the pi overlap is quite dominant, isn't it?
Yes, it happens before
Because-
6.
Yeah, so because it's such a small space, because the atoms are so close that the lobes of pi overlap more, you can say strongly, and therefore the split will take place and the pi will acquire the pi star, the pi and pi star, how you represent. So for less than 14, we have a different order of energy, isn't it? But for more than 14, we have a different order. Okay. So this is the molecular orbital theory. But when you go from molecule to crystal, it is like superposition of infinite atoms. At least if I go by the neighbors only, at least I can say every atom will in the influence of 6 neighbor atoms, right? Imagine it's a 3-dimensional cubic cell structure. So every atom will have how many neighbors? Minimum? Come on, tell me. How crystals are
least
formed?
At least
See.
6.
See, crystals are formed when atoms come even closer. So the atomic separation of crystal, which we call crystal spacing, which I have discussed in Bragg's law of reflection. The atomic spacing is so small that their individuality, those atomic orbitals, will lose the meaning. All the orbitals will overlap to each other. And now the electrons are confused. Do I belong to this neighbor or that neighbor? Is it my house or their house? It is like in earthquake, all the neighboring buildings collapsed, and it is difficult to identify the rooftop, that whether it belongs to me or yours. If you go to small cities, you must have seen, at least in movies, thanks to Bollywood, in that context, that the neighbor's rooftop is very, highly accessible from the other's neighbor, right? You can go from one neighbor to other neighbor just by jumping. And most of the scenes are shooted that way only. So they jump from one roof to other roof and then to other roof, because every roof is available to the thief or whatever, the hero or the villain. So if you imagine the person as the electron and this roof as the energy values, so can we distinguish which energy belongs to whom? And the answer is no. Okay. So there, the energy level, which was a very fine defined boundary, that boundary has become blurred, because my boundary, your boundary, and everyone else's boundary has overlapped with each other. So coming to form a crystal means a large number of infinite atoms coming closer, and they disrupt the energy value of the outermost shell. Now, luckily, the kernel shell still remains isolated. So in the formation of crystal, the kernels are not disturbed. Only the valence shells are disturbed. And instead of one particular energy value, they acquire a range of value. And this range of value, what we call band. So the word band means, so how we represent orbit? Like this. So if all will overlap much together, what will get? You get a cluster of energy levels coming together. So when you draw something like this, what we name it? Band. So that's why we have something called band theory of solids. And in band theory, the energy values are so closely spaced that it is impossible to understand that they are distinct. So now that's why we call a band of energy. And electrons are free to stay in this band instead of the orbit. And the band will, band means what? They can stay here also, they can stay here also, or here also. So now they are free to live in the entire band space. Okay. So I think it's not getting late for many of you. So I'll continue this discussion of band theory in the next lecture. All right, guys.
Okay, sir.
Yes, sir.
Or should I complete this band part? I mean, if everyone is comfortable, I can continue.
Yes, sir.
Yes.
Okay, fine. So the band is very simple. Banding means from Bohr's world to the crystal world. If you keep on moving from here to there, the superposition or superimposing atoms will grow, keep on growing, and therefore you have to reject one theory. You have to bring a new theory. So we had Bohr's theory for isolated atom. Then we have MOT for atomic orbitals, and all are based on the same philosophy. Everything is simply creation of standing wave, nothing more, nothing less. Okay. So MOT is also superposition of wave, which means you again create a standing wave, but this standing wave will become, they will degenerate from each other and will create two separate energy levels. Okay. One is low, other is high. Okay. So we'll come to the same idea here as well, like how it goes. Okay. So when atoms come closer, then if you pull out the graph of energy versus the lattice spacing, you will see something really interesting. So if I plot a graph between the energy between the lattice spacing, okay, or you can say interatomic separation. So if you actually do the interatomic separation, what will happen? The kernel shell. Okay, now let's talk about the carbon. Carbon. What is the configuration? 1s2, 2s2, 2p2.
Yes.
Yes, sir.
So how we draw? One box, then another box. Then how many boxes we have?
3.
How many person? 2. Oh, sorry.
Yes,
You
sir.
mean 1 and 1?
1 and
Yes. Yes.
Yeah, correct. But in case of carbon, what happens? This will jump to here, and what you get is instead of 2 unpaired, how many unpaired you get?
4.
4. So it goes with the philosophy of half-filled and full-filled orbital, right?
Yeah.
So the half-filled orbitals are more stable than this partially filled. So it will prefer this kind of configuration. Now, what you need to realize that every box represents 2 states. Okay. So how many states we have here? 2, 2, 2, 2, 2. How many? State. So this is completely filled state. So we can ignore this state because this is the kernel. Because the valence shell is how much? The 2 only, no? 1 is kernel.
Yeah.
This is valence. And what I said, which one will overlap?
The valence.
Only valence will overlap. Kernel will be unaffected, right? So this part of the configuration is unaffected due to what? Overlapping of atomic orbitals. So now come to this part. How many states we have? If you count here,
8.
8. So we have 8 possible. You can say every room is twin sharing basis. So we have how many beds to accommodate? So we have 8 beds to accommodate, but how many guests are there?
4.
So we have only 4 guests. Okay. So if you combine n such atoms, so for n atoms, how many states are available?
8 in
And how many guests are there?
4.
So just remember this part, 8 in states and 4 in guests. So if you draw the 2s and 2p, and just because of carbon, it's easy to answer. I can say ns and np, that's in general. So something ns and something, because we are doing it for the which
Valence.
valence shell. Okay, so n will come. So as you go in the smaller part of the separation, the energy gap will start converging. So eventually this will converge. But beyond this, it will further diverge. So it will converge, and beyond this, it will further diverge. We can draw something like this. Let me fill with some color. You can see that the orbitals which are isolated, they lose their identity and they converge first, and then they split it beyond certain separation. So I hope you can see the splitting part. So what is happening?
Yeah.
Because see, I'm doing for n states now, so n atoms will converge, and then if you keep on decreasing, I mean, see, you're not decreasing actually. It is already found in nature. So crystals are so small in terms of separation that they belong to this part of. They belong to this part of spectrum. In this part, do you see something? You can see something. You can see this part, he is having this layer of energy and this layer of energy. How many states we had? 18 states.
8 in straight.
So this, as we come closer, it will degenerate into foreign state here and foreign state. Yeah. So out of, and this separation D is the separation already found for lattice. So lattice will have this range of separation. So you can see the energy values will be something like this. So out of 18 states, we have a splitting of state. So you can say 4 bits are now high price and 4 bits are low price. And how many guests we have?
4.
So the nature will prefer which price, high price or low budget one?
High.
Nature will prefer which, low price or high price?
Low price.
Low price.
Low price. See, unless, I mean, if you're having the love for the luxury, of course you can go to high, but nature always goes to the lowest energy configuration. See, configuration must be lowest to be more stable, isn't it? So
Yes.
out of 18 states, there is a splitting of the state into energy and high energy and low energy state. And how many electrons we have? Only 4, no? So all four will go where?
Low energy.
The low energy state. So this low energy state we call, what we call? This is called VB,
Valence band,
and this is called
conduction band.
CV, conduction. So VB is called valence band, and CV is called conduction band. And you can see that a semiconductor having the crystalline structure, all of the guys living in which band? Valence band. And therefore they generally do not conduct electricity. They are as good as insulator at a very low temperature. So if you come to the sub-zero temperature, if you are close to the 0 Kelvin, a semiconductor is as good as what?
Insulator.
Insulator. And this gap for semiconductor, but there is something we are lucky. This gap for the semiconductor is found to be less than 3. Oh. So this is called energy gap. We call EG. And this energy gap at 0 degrees Celsius, at 0 Kelvin, is found to be how much? Less than 0.3 electron volt. Understood? Not 0.3, it's 3. No mistake. It is 3. So this gap is found to be less than how much, guys?
0.3.
No, 3 electron. Okay. Now this energy is something which we can achieve at common room temperature. Understood? So even at a room temperature, this energy can be achieved. And once you achieve this energy, some of the electron living in the low energy state will jump to where? The conduction band. Understood? So there is a jump of electron from which band to which band? Valence band to conduction band. And that is how, as you move away from the absolute 0 temperature, as you grow in temperature, at normal room temperature, you will always find some guys leaving the valence band and living in the conduction band. And it is those electrons in the conduction band which conduct electricity. Is this clear what I'm saying? Hello.
Yes, sir.
Yes.
Yes.
Now, generally, we don't draw this complex diagram, rather we draw a simplistic diagram. So as I said, it's a band theory. So we draw like a band. So generally, if you read any book, you will see 2 rectangles are drawn. So these rectangles has come from that diagram, actual diagram. Okay. So you have 2 rectangles. This is how we draw it. This is called energy gap. You can call EG. Energy gap, and this energy gap is what? Less than 3 electron volt. Understood?
Yes.
And this is for semiconductor. So who are insulators? Who are insulators?
Large energy gap.
Having more than these 3, right? That's it. Now the upper value of valence band. So the maximum energy of valence band is called EV, and the minimum of conduction band is called EC. So I think it is self-explanatory from the diagram, right? What is EV and what is EC?
Yes, sir.
Okay. So if it is semiconductor, then the condition which is required is that EG must be less than 3 EV, 3 electron volt. Then it is semiconductor. So who are conductors? Who are insulators, by the way?
EG larger than 3 EV.
That's it. So by definition, as per the band theory, we call insulators those element whose energy value exceeds the 3 EV range. So if this value is exceeding the, we call insulator. So now what do we talk about the semiconductor? In semiconductor, the valence band is completely filled or partially filled or unfilled, I mean empty.
Completely full.
So in so you must remember that in semiconductor, valence band is completely filled and conduction band is empty at 0 Kelvin. But as the temperature will grow, then what will happen? Some of the valence band electron will jump to the
Conduction band.
So it is quite possible that the electrons residing here, after acquiring some energy, can jump here. Now you may be wondering that say, is it such a big energy, 3 EV, that we are bothered? See, I can give any energy they can ask for. Okay, I have too much energy. The answer is no. This 3 EV is the energy for one particular, you can say, atom. So giving every atom this much is a tremendous energy. It's very difficult to, break down the energy to each individual atom. So you may give a lot of energy to that, but that energy will remain only at the surface. Okay. So giving energy to individual level of 3 EV is a big challenge. It's not very easy. So even we can give energy to insulator also. Insulator becomes conductor. That's also possible. In that case, you just there is something called the dielectric breakdown, which we studied in electrostatics, right? So even air becomes conductor, right? You simply tear apart the atom, you release the electron, you make the medium conducting. Okay. So this is called energy gap. There is other name also, forbidden energy gap. Forbidden gap and so on. So these all are names you should be aware of. Insulator, it is more than 3 EV. What about the conductors? If I go by the band theory,
The bands
how-
overlap.
yeah. So in conduction, in conductor, some valence electrons are always in the conduction band, no matter what. So although even those who live in the valence band, they by default also live in the conduction band. This is the overlapping region, right? So this electron belongs to both. It means at every instant you will get some electron in the conduction band ready to conduct. Okay. And that's why I said the problem with the conductor is they don't have threshold. So the whole idea of threshold is meaningless in case of conductor. So band theory is clear?
Yes.
Okay, it's not a big deal. I'll also write it down. This is called the completely empty at 0 K, and this is completely filled, right?
Yes.
I hope this is clear. This is not a big deal. Okay. So now there is one more energy gap which you need to be aware of. There is one more terminology which we use, and that is called the Fermi energy level. Fermi. Now it is not called gap, it is called energy level. Fermi energy level. So we write as EF. So what is Fermi energy level? It is exactly the midpoint of energy gap. So the way of writing is it is the sum of EC and EV by 2. Okay. So you can think like, okay, those electrons having energy more than Fermi energy level will have more probability of going into conduction band, isn't it? So if the electron is somewhere here, the chances it will go make a transition in this way, then downward, and the electrons which are here will try to go this way, preferably more than above. Okay. So it is like a, again cutoff. It is the threshold that if you have energy more than this, the chance of going into the conduction band will grow in value. Okay. And if the value is less than EF, then the chance of coming to the valence band is more. So it's like a kind of a probability estimation based on energy. That sorry. That is which electrons are more probable to go to conduction band or to valence band. Is this clear, guys? Tell me.
Yes, sir.
Yes.
I will not talk about the conductivity of semiconductor because I have discussed in current chapter directly. So I have discussed about the in current drift, diffusion, and holes, mobility, and everything else, right? If you remember. So it is a good time you can go and watch that first or second lecture. The first 2 lectures will have everything which I have discussed today. Not the first lecture will have that conduction part. Okay. So I hope you remember this conduction part. So conduction, okay, I just started from conduction will have the contribution from. So conduction of semiconductor will be mod of, tell me what? Mu E Ne plus
mu
mu
h.
H NH. It could be minus also depending on if the holes and electrons are in the same direction or in the opposite direction. So if it is opposite, it is plus. If it is same, it's minus. Okay.
Yes, sir.
All right. So I'll quickly mention the types of semiconductor which I have discussed before. Types of semiconductor. How many types we have? Quickly, we have 2 types: intrinsic and
Dope.
extrinsic or doped. Yeah. So what is doping? It is the process of addition of
Impurities.
desirable impurities
Mm.
in order to increase the conductivity of intrinsic or pure semiconductor. Okay, all these things you can keep in mind. Okay. So for a pure semiconductor, the concentration of electron or concentration of hole are equal to each other. We call it Ni, the intrinsic concentration. That's why the symbol, the subscript I, this is called intrinsic concentration. Okay. But in case of doped semiconductor, things will change. Okay. So here we have 2 types of doping. So doping to create P type and doping to create N type, right? So there are 2 types of doping process, which we say ND and NA. What is ND? Donor concentration. What is Na then?
Accepted.
Acceptor concentration. So who is donor? The one who donates electron is donor. The one who donates accepts electron is acceptor. So if you remember, the group 5A elements are donors and 3. Because if you remember that when you added the 5A, it give off electron here to the conduction process, isn't it?
Yeah.
Yes.
So the one who gives electron for conduction are donors. And you can see here, this 3A has absorbed electron, or you can say given holes. So the acceptor and the donor nomenclature based on the one who gives electron, the one who accepts electron. So group 3A are, who are group 3A?
Electron acceptors.
Yeah, so group 3A are acceptor and 5A are donors. Okay. So there is something called mass, it's Einstein mass action law. So what Einstein said, he said that whether you dope or you keep it pure. So what he said that the product of concentration of electrons and hole in any semiconductor remains constant at a given temperature. So what is the statement of this Einstein mass action law? The product of holes concentration and electron concentration remains same for all intrinsic as well as extrinsic semiconductor, that is, it is unaffected by doping process. So doping is a phenomenon of addition of desirable impurities in order to increase the conductivity of a semiconductor is called doping. The added impurities are called dopants, and the semiconductor thus obtained are called extrinsic semiconductor. Okay, so the P type is clear, N type is clear. So what is the law of mass action in mathematical form? So we say if it is pure semiconductor, then we can say the Ni, so hole is also Ni and electron is also Ni. But when you dope it, they will have different value of Ne and NH. So this remains constant. So the formula becomes what? Quickly, I'll mention here. The formula is NeNH equals to Ni square. Okay. So addition of donor. So when you get a question in which you know the how many donors you added, so they will give you ppm, parts per million. From there you can find the answer, and they will also give you the Ni value, the intrinsic concentration. So addition of donor atoms. So how to get? When you have the donor, the Ne will be equals to Nd. We replace the electron by donor atoms concentration. Okay.
Yes.
Okay. So unless you will not see the mathematical relation, you will not come to know why I'm writing like this. It is why I'm writing roughly because the reality is it will grow in value. So Ne becomes in reality Nd plus Ni, like what you had initially. But if you realize that the Nd turns out to be much bigger than Ni. And what I think Hasika said in the beginning, that if you add parts per million, Okay. Parts per million. It is 10 power how much? 10 power 6. Correct?
Hmm.
And the general concentration of atom is 10 power 28. So 10 power 28 upon 10 power 6. How many atoms you have added? This is ND. What is Ni? I said Ni is 10 power 16. So adding 10 power 22 and 10 power 16, then we add this is roughly 10 power 22. Okay, you're not getting it because what place of decimal we are changing? After 6 place of decimal, isn't it?
Yes.
So technically, although it's a big number, but compared to this number, it is nothing. And that is why the NE, when you have the donor, the total number of concentration will actually grow. But as I said, ND is much bigger than NI. And that is why we roughly take NE as ND. And therefore, if you apply the mass action, what is the concentration of hole in this case? Okay, that's very simple. Similarly, addition of a acceptor, what will give you what answer? So if you add acceptor atom, then what will happen? The NH becomes Na. The whole is same as Na. Okay.
Yeah.
In that case, the Ne will be how much? Ni square by N. That's it. So this is the law of mass action. And quickly, I'll add one more topic, then we'll end today's lecture. So band theory is over. So the next is what is the effect of acceptor and donor on the energy level values? So effect of addition of acceptor and donor atoms in energy value. So donor donates what? Electron or hole?
Electron.
And electron we can directly use for the conduction purpose, isn't it?
Yeah.
So if this was the original, this is the original energy gap. If this was the EC, if this was the EV, a donor will facilitate the conduction process, yes or no? Tell me, guys.
Yes.
So we say that a donor lowers the conduction band energy. Okay, so it will go down. So when you add a donor will lower the EC value. Now people can climb easily to the conduction band. This is how we think. So the transition of electron from the valence to conduction will be easier now,
Yes.
isn't it? But the question is, it is now easier due to the lowering of EC. So now the EC dash is here. So can we say the Fermi energy level will also decrease or will lower down?
Yes.
So now the new value of Fermi energy level will be how much? EF dash.
EC dash plus EV by 2.
So they will ask you question that what happens when you add donor? So answer is it decreases the lower limit of conduction band energy. So it simply lowers the conduction band energy. Okay. And that is how it will facilitate the conduction process. So what will happen to the acceptor case? You can draw the analogy similarly. So this is conduction band, this is valence band. So when you add acceptor, it will not affect the conduction process, but it will increase the valence band energy level. And that is why it will again facilitate the conduction process. So the transition will be smoother than before. But what you need to realize that acceptor is doing by different process. So both will increase the connectivity of the pure semiconductor, but both will do it in a different process. Do you realize this what I'm saying?
Yes.
So of course the extrinsic will have more connectivity than intrinsic, but with two different method of donor and acceptor, the mechanism will change. And of course, the Fermi energy level will also change. So what is the new Fermi energy level here? EC plus EV dash by 2. Okay.
Yeah.
So in both cases, the difference between EC and EV will decrease, yes or no?
Yes, sir.
Okay. So whether you add the conduction, whether you add donor atoms or whether you add acceptor atoms, in either case, the energy gap will decrease. So can we say extrinsic semiconductor will have lesser EG than intrinsic semiconductor? Tell me guys, yes or no?
Yes, sir.
Yeah.
These all are theoretical questions that you will come across. That's it. Okay. So, okay, I'll be sharing with you the complete practice sheet. But I think this sheet will also, which I have shared today, it is already having this all the questions. So right now you won't be able to solve much question, but yeah, this is the base of semiconductor physics. If you understand the conduction band, valence band, band theory, that is sufficient to play with the idea. Okay. So, okay, next class I'm going to start the PN junction diode. So let me put a heading so that when you come back, you can just let me know. PN junction. Okay, so we'll move slightly slow here. And once you are done with the concept, you can again move fast. Okay. So total we have 25 pages, and out of that you have studied 5 pages only. Okay. So anyway, I'll try to increase some more lectures this week as well. Okay. Bye guys. Take care. See you tomorrow. Tomorrow is also lecture, I think, extra lecture.
Yes, sir.
Yes, sir.
Good night, guys.
Thank you, sir.
Bye, sir. Thank you, sir.